Alright, welcome back to Anton Math. Now this is the last video of Part 5, Unit 4 of our pre-calculus section. And I just want to go and do several examples, one of each of the type of the new functions that we learned to graph in this section, with all of the transformations and shifts and everything that we learned about when we were looking at the sine and cosine graphs. Alright, now the one I want to start with is tangent. Let's start with our first example. Now I want to look at the equation y equals tangent of 2x minus pi over 2. Tangent of 2x minus pi over 2. Now my general form for this equation that we want to get it into to find all that information that we found in the last section. It's going to be just like the sine and cosine. We're looking at y equals a tangent of k times x minus b. Right, now just like before, a is going to be my amplitude, the absolute value of whatever is here. K is going to help us determine our period, and b is going to help us find our horizontal shifts. Now first I want to get this equation into my general form. That's always what we do first when we're graphing any kind of trigonometric equation. We want to get it into our general form so we can start identifying these different components. So we're almost there already. My a is 1, so nothing really to worry about here. I have this tangent. Now what I need to do is, inside of here I need to get my x alone. It needs to have a coefficient of 1, and it needs to be a positive 1, right? And this is a pretty easy one. All I need to do here is factor out a 2. So this will be y equals tangent of 2 times the quantity x minus, now remember I also have to factor out that 2 from pi over 2. So it's going to be pi over 4 here. Alright, and we're ready to start getting some information. My amplitude, absolute value of a, is equal to 1. So we're not looking at stretching the tangent curve up or down any. My k is equal to 2. So that gives me a period of, now here's where it gets a little bit tricky with tangent and cotangent. Remember that with tangent and cotangent, my base period of pi is pi. So my period function is not 2 pi over k, but just pi over k, right? I'm still dividing my base period by k, but here with tangent and cotangent, my base period is pi. So that's going to be pi over 2. So pi over 2 is going to be the total distance of my single period of this graph. All right. Now we also have one more piece of information. I have that b equals pi over 4, right? That negative is a part of my general formula. So b is not negative pi over 4, b is a positive pi over 4. So that b being positive pi over 4 means I'm shifting to the right by pi over 4, right? Shifting in the positive direction by pi over 4 units. All right, now let's put this all together. Now tangent can be a little bit tricky because the order of how you do things kind of matters a little bit. Now, and it depends on how you think about it. How I like to think about it is I base everything off of the middle. I know that the middle of tangent is usually at 0, 0, right? It crosses through right here. Now any period change isn't going to change that. I can use that as kind of my basis for the shift. So that means that my center of my new graph is going to be here at pi over 4. Let's go ahead and denote this is pi here, this is pi over 2. So this is pi over 4, right? I've shifted my center to the right. Now the reason that I do that instead of shifting my left is that when the period changes for tangent, it's a compression or a stretch from the center, right? Let's just say I didn't have a shift at all and my period changed to 2 pi. Well, my center would still be here at 0, 0, even though one base, if you go back to the tangent video, you'll see that we went from negative pi over 2 to pi over 2. It's very important that you do not shift the left asymptote and then stretch and skew. Your graph can get off in that way. When you do the shift for tangent, keep everything based around that center point and you'll be good to go the whole way. All right? So now looking at this, if my center's at pi over 4 and I have a total period of pi over 2, that means that my period is going to stretch in pi over 4 from the center in either direction, right? The total period is pi over 2, so from the middle, it's pi over 4 in either direction. So that means that my interval of one period is just going to be from 0 to pi over 2. Right, so again here, the b to b plus the period formula doesn't work for finding the interval of tangent because our period usually stretches off to the left to begin with. Okay, so 0 to pi over 2, that means that my left asymptote is going to be at 0. My right asymptote is going to be at pi over 2. And then we can just kind of draw in our tangent, right? Coming up here and coming back down. If you want to be really accurate, you can find the point where tangent equals 1, and that's going to be at the 3/4 mark, and tangent will be -1 at the 1/4 mark. So that would actually, looking at the way I've drawn the graph here, that's going to put 1 at about right here. We'll do it kind of the backwards way, right? -1's about right here. Okay, so here we go. This is my tangent of 2x minus pi over 2, or tangent of 2 times x minus pi over 4. Okay, now in this next one, we're going to look at a problem with cotangent. Clean this up a little bit. Problem 2. Let's look at y equals cotangent of pi minus x. Right, so again, my general formula, I'm trying to get it to look like y equals a cotangent of k times x minus b. Okay, and we're almost there already. My a and my k are both 1, so we don't have to worry about anything there. But I do have this negative x. So we need to remind ourselves, is cotangent an even function, or is cotangent an odd function? And if you remember from our previous videos, we determined that both tangent and cotangent are odd functions. So this is the same as cotangent, and I can factor out that negative, right? Negative x minus pi. But because cotangent is odd, cotangent of a negative value is the same as negative cotangent of that positive value. We do need to always get rid of this negative, right? My k, even though it's 1 here, it needs to be a positive 1, not a negative 1, or that's going to throw us off later, right? This negative needs to be accounted for. So this is going to be equal to negative cotangent of x minus pi. All right, so my absolute value of a is 1, so I have an amplitude of 1. My k is equal to 1, so my period, remember with cotangent, is pi divided by k. So in this case, it's just pi. And I have a shift, or my b value rather, is equal to positive pi. So I have a shift of pi to the right, don't I? I'm shifting to the right by pi. Now this is a little bit interesting. I have a period of pi, and I'm shifting to the right by pi. So let's take a look at this. I'll do it the way that we've spelled it out here, and then we'll observe something. So if I've shifted to the right by pi, that means my new interval is going to be pi to pi plus my period. We don't have to worry about anchoring cotangent the same way we did tangent. If we keep that left asymptote, which is on that y-axis, and generally for all of these functions, when you're considering shifts, think of it as you're shifting whatever is crossing this point, x equals 0. That's a pretty safe way to do it in general. My interval is going to be pi to pi plus the period, which is also pi, so 2 pi. So I have an asymptote here at pi. I have another asymptote here over at 2 pi. I know that cotangent passes 0 in the middle. And now we need to take that negative into consideration, right? Don't forget those negatives. Usually cotangent starts from the top and then goes down, but here it's going to be starting from the bottom and coming up. Looks like tangent, doesn't it? Now here's what I wanted to observe after I draw this. this has a period of pi and it's shifted to the right by pi. So let's just say that I kept drawing my graph over here to the left. Well, it would look like this, wouldn't it, if I just kept going? Remember, we can use that rubber stamp and just keep drawing these. Well, this is just negative cotangent of x, isn't it? So it turns out cotangent of x minus pi is the same thing as cotangent of x, and we'll get into that deeper in the upcoming chapters. There's a lot of formulas like this that come in very handy. All right, I'm done with that example. Let's take a look at secant and cosecant now. And the first one I'm just going to draw based on that base graph that we made, and then the second one I'm going to show you a little trick. There'll need to be some explanation. I don't like, I like showing tricks, but I want to make sure you guys understand what's going on when I do. So first, let's look at this problem 3. Problem 3, we have y equals 2 cosecant, and then in the parentheses, pi x minus pi over 3. We're a little bit out of our comfort zone here, but that's okay. Pi x minus pi over 3. Now I want to get this into my general form. I'm not going to write it up. I think you guys are used to what this looks like now. So I need y equals 2 is my a, cosecant. Now I need to get x alone with a coefficient of positive 1. So I'm going to need to factor out a pi. And then I have x minus, I need to factor out a pi from pi over 3 as well. So it's going to be x minus 1/3. Okay, so we're transitioning a little bit here. Now, first of all, my amplitude, absolute value of a, that's just absolute value of 2, which is 2. My k is equal to pi, isn't it? So my period is equal to, remember, cosecant has a base period of 2 pi. It's going to be 2 pi over k, or 2 pi over pi. So my period is going to be 2. All right? So you kind of see what I've done here. I've transitioned. We've switched where we're using pi's and where we're using real numbers. So I'm going to mark my graph here. 1, 2. Okay. Now I have a b equals to positive 1/3, don't I? So I'm shifting to the right by 1/3. All right, let's take a look at what this looks like. I've shifted to the right by 1/3, so that means that my interval is going to be from 1/3 to 1/3 plus my period, which is 2, so that's going to put me up at 7/3, isn't it? Remember, 2 is the same as 6/3, so adding 1/3 to 6/3 gives me 7/3. So 1/3 is going to be about right here. And 7/3 will be about right here. I'm getting off my screen a little bit. So let's go ahead and draw this out. With cosecant, well first let me put a midpoint, sorry. Point will be right here. With cosecant, I know that I have an asymptote at the beginning, an asymptote at the end, and an asymptote in the middle. Right, just like sine, remember the asymptotes of cosecant correspond just like the zeros of sine, right? It has that same pattern. Now I have an amplitude of 2, so let's call this 1, 2 on my graph. That means that whereas where sine, the amplitude meant that's the furthest away it got, with cosecant and secant, amplitude means that's the closest to that center horizontal axis that you get. Right? I'm basically taking that base graph of cosecant and I'm multiplying it by 2. So it's getting further away, isn't it? So that means here in this first quarter point, I'm going to be up here at 2. And down here at this third quarter point, I'm going to be down at -2. Right? So even though it's going to be cutting down in the bottom, I think you can see what it's going to look like. My cosecant graph is going to look something like this. Right? Goes up in this first step, and then goes down, approaching those asymptotes down here. All right, so there's my 2 cosecant of pi. Now I want to make an observation here, and we'll use this to actually graph out the next one. Let's say that I was looking at the graph y equals 2 sine of pi x minus 1/3. Now the amplitude and the shifts and the period and everything we already found out is going to be the same for this as it was for our actual problem 3. So I'm going to be starting here. I'm going to be going up, hitting this point, and going down and hitting this point, aren't I? All right. So why is this useful? Well, let's take a look in the next example, kind of leading into this. This is a useful trick, especially if you're very comfortable with sine and cosine, and you're not quite sure what your cosecant or secant can look like. We can use sine and cosine to very easily graph this cosecant and secant. All right, and we'll do that here in problem 4 for our secant problem. So problem 4, y equals 1/2 secant of 2x. All right, this is my problem. I made it a simple one because I just want to illustrate this point and this tool that we can use. So first of all, I'm already in general form here, aren't I? There's nothing really to factor out over here. Everything looks good. So I have an amplitude, which is absolute value of 1/2, or just 1/2. I have a k is equal to 2, so my period is going to be equal to 2 pi over k, or 2 pi over 2, or in other words, just pi. And I have no b. My b equals 0, so no shifts. All right, nothing to worry about here. Now what I want to do here is I want to actually look at the graph first. I want to look at the graph y equals 1/2 cosine of 2x. I know that secant is 1 over cosine. Now it's very important here that I say something. I don't want to mislead anybody. 1/2 secant of 2x is not equal to 1 over 1/2 cosine of 2x. This just is not true, right? This is equal to 2 secant 2x on the right-hand side here. I'll let you work that out for yourself, but I just want to say I'm not looking at the graph that is the reciprocal of this secant. That's not what I'm doing. I'm looking at the graph of cosine that has the same amplitude, the same period, and the same shifts as secant. And that way, I know that my amplitudes are going to match up at the same point. My asymptotes for secant are going to match up to the zeros of this cosine function, etc., etc. So I can use it as a blueprint to find secant. But it's important to note that this is not the function that 1 over this equals this. That's not how I found this function. I'm just looking at the cosine graph with all of the same attributes as on the left over here. Okay. So that being said, now we can use this as a tool. I'm going to graph this function, y equals 1/2 cosine of 2x. And we already found the amplitude, the period, and the shifts, right? We're already done with that part. So let's call this 1 right here, right? I want 1/2 to be easy to see. I have that my period is pi, so let's just call this pi here, give us some room to work with. So this is going to be pi over 2 here. I know that my cosine is going to start up at 1/2. It's going to bottom out at negative 1/2 in the middle, and it's going to peak out at 1/2 at the end. And it crosses the horizontal axis at the 1/4 and the 3/4 point, right? This is my graph 1/2 cosine of 2x. Now I can use this graph to find my secant graph the same way that we derived secant and cosecant, right? Everywhere that this cosine is equal to 0, well, that's an asymptote for my secant. And because they have the same amplitude, that means that this point is shared between both of them. And it's the peak of one and the bottom of another, isn't it? And here vice versa. The bottom of one and the peak of another. And there we have it. So on a test or on a homework or something like that, where I've drawn this dark blue, I would suggest if you're going to use this tool, just draw a very light dotted line with your pencil where this cosine or sine would be. Then you can draw in your secant or cosecant graph solid, and then just erase this part at the end, right? You don't want this to really be here on your final answer because that's not part of the graph, okay? If I had thought enough ahead, I would have layered it so that I could do that, but what I mean is we would just erase this part here, right? We don't want to leave that on any assignment because that's not part of our graph. That's going to be misleading. But here we are. That is my final result. This is y equals 1/2 secant of 2x. All right, well, good luck on your homework and your assignments. I hope that this video was helpful, albeit a little bit long, and we'll see you in the next section.